Hello everybody, good afternoon. We'll begin the lecture number 2 in the session on problem solving in C with pointers. So I am going to use a fresh set of slides. If you have any doubts about the last ones, then we'll discuss it. Let's begin with the first slide. The motivation for these one or two slides which are given is basically to tell you that when you use a pointer based application, then it's very important that you know the language that you are choosing. Okay, so these two slides simply tell you that even though C and C++ come from the same family, they are essentially development of one language over the other. They are reasonably different. They are significantly different when it turns out to what is known as type checking. So look at the first one. The first line says int I equals 0. The left hand side object is I, which is int, assigned a value 0, which is also an int, so this is fine. The second one, to continue with the previous style of discussion, defines an entity called IP, which is a pointer to integer. IP is int star. On the right hand side of IP, we have address of I is an integer, address is the operator taken, so it's also int star. So this goes through without a problem. The issue is about the third statement, which says int k is an integer, the RHS is IP, the type of IP is int star. So an integer is assigned a pointer. Okay, it should get a value, but it's getting an address. So let's see what the two languages do. I use the GCC compiler. So these are all on my laptop. Whatever errors are given should be similar mostly for your system too, but there can be minor difference. So C says warning, initializing int, which is k, with a pointer without cast. W is a short for without. You are trying to get a pointer converted to an integer. It gives you a warning, but the unsafe part is it allows the program to go through, produces an executable a.out, it will run, and it may give you problems of a different. If you look at C++, it says, you can see error, invalid conversion from int star to int. Int star is the right hand side, int is the LHS, and an error means this program cannot be run unless you correct the error. So when you use pointers, the moral of the story is, if you are using C, you will be allowed to do a lot of unsafe assignments, whereas in C++ the chances are the errors will be pointed out, and unless you correct them, they will not work. The second one is similar. UIP is a pointer to unsigned int. So what is UIP? Is unsigned int star. The kind of addresses that you can put in UIP should be those of unsigned integer entities. And this is assigned IP. You go to the second line on top of the slide, IP is int star. So this assignment essentially is unsigned int star equal to int star. Same family. One is unsigned, the other is signed perhaps. C accepts, doesn't even give you a warning. C says, okay, go ahead, your problem. C++ says, no, there's an error, please correct. You cannot, it will not let you go unless you use something called a cast. You can temporarily convert a pointer from one type to another, knowing the attendant risks, and then it goes through. So similarly, if you look at the next slide, you can see that similar things are happening over here. I will not take too much of time. I'm sure you can read it out and understand and see the difference between C and C++ quite explicitly. So what I'm summarizing is, when you choose a language with care, because it may give you a big help in finding out your errors and warning you or actually stopping you, whereas another language may let you go through and errors will come at runtime. It's always good to get the errors caught at compile time for anyone who is writing reasonable program. Okay, so let me move on. So you can create many such examples in C++ and C to note the differences. This was just a point to some such example. The next slide, I talked about it the last time, so I just skip through. I thought I'll put some pictures out here. So I'm really concentrating on this slide, which is the slide number 6, which talks about pointers and runtime error. So the statement on the top is not always true. It is not necessarily a segmentation fault only because of a pointer, but in most practical scenarios, they are often the cause. So when it happens in most Unix Linux based systems, you get this error which I have written out there, segmentation fault bracket core dump. Okay, so what does it mean is written out below. I talked about it last time. Segmentation fault occurs when a process, which is a running program, attempts to access a memory that does not belong to its own address space, and when one does so, the OS, the operating system, mercilessly terminates the process and throws us out. So that's the meaning of segmentation fault. You are not in your own area, you are trying to access an area outside your own process. The core dump is basically a file which gives you some information about what happened around the time of the segmentation fault and why is it produced. Because typically a debugger can make some sense out. Okay, so the core dump is not something that I and you can use, but if you are using a debugger, the code dump can be examined by the debugger to give you more reasonable idea about the nature of the fault. So in general, I want you to be aware, probably you already know, that segmentation faults are fatal errors. The program is abnormally terminated. Okay, and then what is to be done, what are the causes, are the immediate concerns of the next few slides. So let me show you the next slide. Okay, so look at this program. It's a fairly simple program. There's only a main program, no other function, single function. There's an integer and there's an integer array. And there is a for loop which runs from 0 to 4999 or 5000 times. And in each iteration of the loop, it prints the value of I, current value of I in the given iteration, and the value which is stored in the array location I. So there are many things wrong with the program, so we'll not worry about it. Firstly, observe that the array A is not initialized. If the compiler is decent, it might initialize. If it is not, then it will not initialize. Yeah, anything can happen. The output is given below. I missed out the first line. I equal to 0 will produce an output. 0 followed by a number, add it on your notes. Followed by, on my system, it shows 1, 0, which means A of 1 is 0, which means that the array was initialized by the compiler. Okay, now observe the problem. Since the loop runs up to 4999, okay, the last value of I, the print keeps on coming. And on one given run, after going to 2122 index value, which gave some arbitrary junk value over there, uninitialized value, the program ended with a segmentation fault. We'd like to examine why. This is not reproducible. Let me tell you again. If I run it again or you run it again, it may happen at 1500 segmentation fault, it may happen at 3000, but more or less it's clear that if you go way beyond the actual size of the array, the actual array that you have declared, which is 0 to 9, some point in time a segmentation fault can come. So I'll show you more faults. So I would like you to know how to generate segmentation faults so we can understand what is to be done when such faults come in an unknown scenario. So this is sort of learning through experience. So let me summarize. And the reason for the segmentation fault is that we accessed A beyond A9, which is the legal size of the array. The regrettable fact is that the compiler did not issue a warning or an error even when we went way beyond 9. It ended in a runtime error. So this is a thing which you can reproduce and check. The values may be different. Here is yet another program. There is no array here. Observe, I've used pointers. So to see what I am doing, I have defined a pointer P, which is a pointer of integer, or it can hold the address of an integer. And K, which is uninitialized, its address has been put into P, whatever that is. There's a loop now which runs over K, goes from 0 up to 3999. Each time K is incremented by 1. Now what is happening inside the loop? Starting in the beginning, P was address of K, right? Some address, 2000, 3000, whatever it was. It's an address. P is a pointer. When you enter the loop, P is incremented with P plus 1. Now something interesting will happen. If P was 2000, let's say the address of K was 2000, just for the sake of argument. 1 is not added to 2000 because it's an integer, and on my machine integers are 4 bytes. 4 is added to P. Okay, so the pointer is incremented by the size of its data value. since it's an integer, p plus 1 is actually changed to p plus 4 by the compiler. And if the initial address was 2000, it now becomes 2003, 2004. And then the printf statement shows you the value of k, whatever that is. And then I try to dereference p. I use the pointer and I say, show me the value which is stored in the address p. Okay, dereference, star p is dereferencing. Since p is a pointer to integer, some integer will come as a result of star p. The object is always an integer object. This strange looking thing called f flush stdout is a C way of saying, please display the output immediately. Flush the output onto the system, wherever, printer, file, whatever, don't delay. Otherwise, what happens often, if the output is not immediately displayed, in case of segmentation fault, you will see no output. So this we are forcing now. I'm saying, show me whatever you print every time. Okay. Now you can see the interesting scenario. When you do p equals p plus 1, okay, the value that you see over here, the values are printed below, is 0 and 10. So can someone sort of figure out why is this value 0 and 10? So maybe I'll try and work it out on my paper. So note down, what we are asking them to print is k and star p, and you can see above the relationship. There are three variables declared of integer type, k, I and j, followed by a pointer. So there are 4 data items in main and the rest is a piece of. Okay, so I'm now going to write on this sheet of paper, okay, and trying to explain this thing a little bit so that you are comfortable with when you mix up things what happens. So in my box style, this is the box for k, okay. I'm assuming something which may or may not be true. K is followed by I in my declaration, which is followed by j. I has the value 10, j has the value 20, and k is uninitialized. And then observe there is a pointer p which is declared and initialized with p is int star with the address of k. So let me assume some address of k and put it inside, right? So before the for loop, this is what has happened. Now when the for loop starts, we assign k equals 0. This is how the for loop starts. So let me put a 0 in k. P equals p plus 1. So p changes to, I'll redraw the value of p. Integer is 4 bytes on my machine. So this will become the new value of p. These are the two things done, and then the program says, please print k and star p. Since the value of k is 0, the first print of k will be 0. And then it says dereference star p. Now we don't know what is star, what is stored at 1004. But you observe what he shows is the value is 10. You can now guess that these things probably by the compiler were put side by side. So when I did p equals p plus 1 and incremented p to 1004, this is actually the value of I. But I've approached it as a pointer to k. So I'm holding on to k, I moved it, I actually reached I indirectly. And this is happening because the compiler has laid out storage like this. It may not have been otherwise. Next time you observe k value in the for loop goes to 1. P changes by adding 4 more to it, becomes 1008. And 1008, if things were consecutive, no guarantee, would become j. And this is the next data that you see. So now you can see what is happening. In the area of the main, here was k, here was I, and here was j. And here is this pointer p, which started with, now let's use the notation, we started with the address of k. In the for loop, you did p equal to p plus 1, it hit I. In the next iteration of the for loop, it hit j. Since I am continuing for some 3099 times as the last value, it will keep hitting these new locations beyond 1004. And some point in time, this will cross the region or the boundary which is my address space. By my, I mean this process address space. And once it crosses, and you try to dereference the p, so the segmentation fault's cause is star p, because we are trying to dereference or trying to figure out what is the value in a certain address, but the address does not belong to it. So pointers you can see here are typically, this is the one possible way in which pointers can give us. Look at the next slide, slide number 9. Okay. So I would like to put a question here. The program is very simple. I'm sure all of you would have written or seen similar programs in exams, tests, okay, wherever. So take a minute to read the program. And the question that I want to ask is, will this program behave properly and give results? It's supposed to be giving us factorial, or will it behave in some uncertain manner, a manner in which we don't want it to work? So if you look at factorial, I've used something which I've done it deliberately, which is static int call equals 0. Okay, so this is a static variable of a function. And just to recall, if you're not remembering it immediately, a static variable of a function does not lose its value when the function is called again. All other things lose their value. So if you look at the typical, code for factorial, it says if n equals 0, return 1, which means factorial 0 is 1. Otherwise, it returns n into factorial n minus 1. This is a standard code which is by and large okay. Now let's look at the main. I put num equals minus 1. It's the initialization as a minus, don't miss that. And then inside the print statement, printf, I'm calling factorial of minus 1 because num is minus. So what do you expect? Factorial of minus 1 will call factorial of minus 2. So then minus 1 factorial is called, which calls factorial of minus 3, is called factorial of minus 4, and this has become an infinite recursion. This will never end. The recursion only ends when n equals 0, return 1 inside the factorial function. But once you have started with a negative value and you are decrementing it, it will reach minus infinity, and maybe then, if you are lucky, it might actually become 0. But that's really, hoping for some magic to occur. So what happens? When I ran this program, deliberately written on my machine, so you can see the solution or the output of the program is given on page 10, where the output of the program is some 1, 2, 2, 6, 1. These are all some values, and then segmentation fault 4 down. Okay. So what exactly is the cause of the problem? Who is causing this? If you go back, I'll answer it all at this after some time. Okay, so let's be on slide 10 itself. The segmentation fault comes. I'll confuse you a little bit. So is it coming because of that static call is being printed on page 9, or is it because there is an infinite recursion? Yes, the calls will never terminate, but why is it showing a segmentation fault? So let me take my CPU cycles. Anyway, I'll answer the questions later. Yeah. So if you go back to page 9, which is currently on my window, the culprit really is this minus 1 initialization here, and this minus 1 is directly being used in the call. Maybe somebody should have said, or I can change the statement here by saying if n less than equals 0, then return 1. Okay, and I can block the infinite recursion. Okay. So I'll give you the answer in a short while. This and similar errors, because of function calls, when it gives you a segmentation fault, why does it? Let me move ahead. I have a few more examples. So let's go to slide 11. Okay, so look at this. I take the gist of it. You can create many such examples to improve your understanding about the layout of memory, segmentation fault, what is your address and what is not our address. So this function, if I quickly summarize, void f1 n10, okay, is a function. This is the main thing or theme of this particular slide. This is a static struct defined. The culprit is that I am going beyond my address space, and in this case address space, if you know, fine, otherwise I'll explain in a short while. I have crossed my static data area. Here is another one which shows that a global data area, globals are declared outside functions. So int A10 is a global. Okay, now inside the main you can refer to A, And just like in the earlier time, I have gone inside, I am trying to refer to this value, to this array address A of I, starting from 0 to 3999, which is way beyond the size of the global. The output below shows that up to 525 value of I, some value was printed as if the array was defined for 525, which is not correct. But when it tried to reach the location 526 of array A, the system 3 was out saying there's a segment. Now there is no magic about 526 or 525. Next time it can be a different value. Okay? These are somewhat predictable, but you cannot be exact. So this is a runtime scenario which I'll explain. And here I have called it global data area and segmentation. Now this is something if you do not know, I'll skip this slide and move on. But you should remember that there are many areas in memory compared to a program, a C program, a C++ program, whatever. And those are, I've given you some ideas here. Data of a function. When a function runs, it has its own data that has to be stored. The function code has to be given memory. Static data of functions have to be given memory. Global data for the entire program has to be given memory, and so on. Okay, and each of these has an implication, typically if you are using pointers also. So this picture should become clear. I skip this. Here I am asking you to write an experiment so that you can figure out what is the address of different parts of this memory. So I create global data and I'll ask what is the address of X? X is global. I create a static inside a function and ask what is the address of the static variable inside the function. Because I can take the ampersand operator and I can take the address of main, I can take the address of another function and ask him to print and so on. Once I do all of that, I get a complete picture of the various objects that are created and where they are in memory. So I'm going to move on to show you a picture. So I'm going to skip slide 16. They are all similar. Skip slide 17 and 18 also, and give you the picture in slide 19, which is the summary of all that I was trying to say. So this is how on my combination, which is a Linux box, Ubuntu, some version of Ubuntu operating system, and GNU compiler, C compiler, which I am using for all the experiments, GCC. This is how the memory is typically organized. So you observe that I have kept some rectangles. So low address means towards the 0 part of the memory. It's not really 0, it is somewhere on the lower address of the memory. The process which I ran or which I typically run, my function codes will be there one after another. So one function code, don't get confused. If I have written 4 functions, there will be 4 different function code areas. This is followed by a single static data area. So it's possible that I have declared 20 static variables in 3 different functions. It does not matter. You can check out the addresses. You will find they are consecutive in some part of the memory, and typically these are called the static data. So static variables of functions are all accumulated together by the compiler and given memory in some part of they are all towards the lower ladder. You should check it out, actually run a program and see. There may be small differences, but by and large the organization is very, very different. After static data, there could be gaps over here. There is a global data. So global data are data which is outside all functions. So the global data is also given contiguous space, even though the global data may be declared at various program points. Before the function, between 2 functions, before main, after main, so it doesn't make sense, you can declare. So global data is again pooled together and put in one part of memory. After that, we'll be seeing today an area which we'll look at called the heap, which is a runtime memory. You can show the direction of movement. And there is a stack. The stack is used for all local data of a function. And as you see, heap and stack are made to grow towards each other. They are given some finite amount of size by the system. It's just a mental model. You don't have to remember the details. Okay. So with this picture now, let me show where our problems are coming. So let me go to my paper. So I'll redraw this small thing over here, but in a slightly different way. I hope you can see this. Assume this is the total RAM on the machine. Assume that these are the low addresses and these are the high addresses. So I'm going to draw smaller rectangles. So let's say this is my main, The code of main is here. There's some gap. There's a code for function f1. Okay. Some gap. The code for function f2. So these are all function codes. The actual compiled code of functions. Above that, there is one single static area which collects all static variables of various functions. Then there could be a gap. Then there's a global area. And then there could be a gap. Then there is a heap. And there is somewhere, this is not the highest part, somewhere here there is a stack. And this is what I have shown. So this is the logical picture. If you remember this, probably you would know where and why a particular problem has happened, typically with compilers. Sorry, pointers. So now, assume that you have access, you have a pointer to the static area. There is a pointer P to the static area. Now this P can look at any address in this range, whatever the range is. But if you take P and do some increment with P, okay, some C, and this C produces an area here, a memory reference here, then this is segmentation fault. It need not go up, it can go down also. Between static and function also there may be a gap of addresses which does not belong to me. So all these addresses are outside my region. It could be actually belonging to some other process. You don't know. These are all, these crossed are not in my region. So if you have a pointer to a static variable and you use it arbitrarily, you can get segmentation fault because you are shooting the static data area. Similarly, if you have a pointer to a global, okay, a global pointer, let's say GP, so long as you are within these addresses, you are fine. You want to go up or below, you will get segmentation fault. However, by accident you reach into heap directly, you may not get a fault because it is still your area. So it's very, very uncertain. Similarly, if you have something on the stack, you have an address or something here. I'll use the example I've already shown you. So you have a pointer or something on the stack, and then you use this pointer to reach way beyond the allocated area of the stack, then again you will get a segmentation fault. So with this simple background, let me explain the factorial program and the problem. So the factorial, now I'll tell you this, maybe you know that for every function, all local data is on the stack. Not only local data, even the arguments to a function are on the stack. There's the only place where the locals are kept. So let me assume now, I'll draw the stack horizontally. Let's say this is my stack. This is the main. So this is the main, means data of main. Main's data is here, whatever that be. And let's say this is my recursive function factorial. Okay. Factorial's data is here. So when we call with factorial minus 1, I don't know if my handwriting is readable. We know that factorial minus 1 will call eventually factorial minus 2. Okay. So for factorial minus 1, this is the call I have shown you. When factorial minus 1 calls minus 2, yet another entry is made on this stack because factorial minus 2 is now running. Factorial minus 2 will call factorial minus 3. So yet another thing will come. So why did the error came? Because finally the system has decided I'll give you some fixed size to the stack. This is a stack. Let's say the stack, just for sake of discussion, was given 1 MB size for every process. So since this is going to keep on growing, factorial will keep calling itself, there will come a point in time when it will try to exceed the space. Some call to factorial will go beyond this, beyond the fixed stack size, which is fairly high, beyond the stack limits. And as soon as it does so, segmentation fault will come. Okay, so the moral of the story is all these areas that I have showed you on your on the slide, which is slide number 19, each one of them is bounded. Function codes have a region, you can't exceed that. Static data is a region, set of addresses. low to high range, consecutive range. You can't exceed that. Global data, you can't go beyond that. Heap, you should be within your area. Stack also, you should be within your area. Anywhere by fault or by design, you try to reach out to addresses beyond the designated sizes. The result is a segmentation. So now you can see the most culprits will be scalars. You cannot ever have a segmentation fault. Scalars are giving fixed place. You can always refer to them as many times as you want, no issues. One problem is with arrays. Because arrays are given a certain size, but arrays are referenced using the address of the first location of the array. Basically, there's a pointer, and the pointer can keep increasing without worrying about where it is going, and therefore it can give you segmentation. Okay, so I hope I've given you a good idea that anywhere from your address segmentation faults are possible, and very badly possible if you are using pointers. So you have to watch out for this error if you are first time programmer. You don't have to worry about it later. Okay, so now I will take a few questions. I can see that there are some things being asked. So before I move out from this, whatever I was doing. So let me summarize. I was trying to get you a feel of segmentation faults, not to just show you that there are segmentation faults, but basically I wanted to draw your attention on this picture 19. Okay, it may slightly differ from architecture to architecture, from the vendor of the operating system, but by and large, what I've shown you is a reasonable organization. Some may flip low to high address. The stack may be at the low address, the function code at the high address, but typically this is what happens on my machine. Okay, so this is a break for questions. Please keep writing your questions. I'll see what has already come. Okay, so the first question I can see is from Lakshmi, who is saying, is it always guaranteed that two integers declared will be given continuous memory locations? No, it is not. So the compiler decides how things will be packed, when the storage is given. What you can be guaranteed is, okay, to answer your question, is this. So let's assume that you are declaring this. To answer this, suppose you have declared some local data. It can be global data, it can be anything. Some data you have declared. So let's say you have declared maybe an int, maybe an array of something, maybe an array of int, which is consecutive. Location arrays are bound to be consecutive. Maybe you have an array of structures, okay, and so on. What you are guaranteed is this. If you take the size, so say let's say this is 4 bytes, let's say this is 400 bytes, let us say this is 800 bytes, or maybe I'll make it bad. Maybe it is 800 and make it a multiple of 7, let's say. Something like this, okay? Whatever. So if you add up all the local data, this will come to, I made my life complicated, 1300 bytes. What you can be very sure is the size of the local data is noted by the compiler, and it will give you some space which is at least 1300 or a little more, because it gives in some units, maybe unit of 8 bytes. It should be a multiple of 8, let us say. If this is not a multiple of 8, let's see if it is not. So it will give you something, maybe. So what is the nearest multiple of 8? Maybe 1304. Just take a look. It may give me 1304 bytes. I'm assuming, these are all assumptions. The memory has decided, the memory allocation unit, that even if you ask for 1 byte, I'll give you 8 bytes, because there's a minimum I give you. So if you need 1300, I give you 1304 bytes. Now in this 1304 bytes, all your data is located. There is no guarantee that the int is first. It's quite possible the array is first, followed by maybe the array of structures, okay, and followed by the array. There may be small gaps because it has given you additional memory, and this is how it's laid out. So what I'm saying is, what is guaranteed is that all your local data is in the space, but you cannot insist by saying the order in which I declared, the compiler should give me in that order, and there should be no gaps, no extra space given. That you cannot guarantee. However, it so happens most often that if you give the same type of data, if you declare 5 ints one after another, the chances very high that they will be next to each other, but it's not a guarantee. And you don't need the guarantee because we never look at memory locations. If I declare variables x, y, z, u, v, okay, I really don't need to know who is whom. I actually refer x by its name, y by its name, address of x if I want to do. The relation between the addresses of x and y are never important, unless it's an add. So I hope that answers the question. Chiranjeev says, until buffer is full, it will continue to run. So this buffer is a very, sort of confusing word over here. Since you said it, let me explain now. Buffers are typically used by operating systems. The compiler has done its job. It has produced object code and vanished. What is running is your target. So the buffer that you're talking about is not very sensible here, because my program, as I showed you, if I go back, okay, so this was a scenario, but that particular, this is about the recursive factorial. So the stack has been given a fixed amount of space, and factorial continuous calls exceeded the max stack size, and it produced an address which is beyond stack and not in my area, not in the heap, and therefore it got into area. So this segmentation fault came because stack size was exceeded. If you want to be very exact. What is memory leakage? Okay, I don't really understand what the question is. Do you mean leakage that in L-E-A-K-E-G-A? So maybe there is some spelling problem there. If this leakage is there, this makes sense. What is memory leakage? I have not reached there yet. But to give you a quick answer, we will be soon talking about the heap memory. Okay. It depends on what extent you know. One should also probably open up the stack memory, but I'll do it on a need to know basis. The stack memory is also very important. One should know what gets into stack, what gets into heap. Our designs of linked lists will take care of that. So what happens is this heap memory, let me draw it like this, is typically used to build different data structures which are dynamic. So without explaining, let me say that I have a tree. Okay, I assume you know what a tree is. Don't bother if you don't. So a tree is here. This is on the heap, and the tree pointer is on the stack. This is very, very important. Something you must have on the stack to reach out to things on the heap. Maybe there's a graph. So these are elements which are related. So maybe there's a graph. These are memory locations. Okay, so don't worry. These locations are linked like this. Maybe this is linked like this. And this graph also has somewhere on the stack, you have an access to the graph. So memory leakage happens when typically if somebody deletes this node or deletes this link. So this has an address. So graph, let's say, has this address 5000, and 5000 is the root of the graph. If you know what it is, great. If not, just imagine this is there. Now somebody came by mistake, made graph equals null. Graph is a position. So I make it as a null pointer. So now this link is broken. So this place graph on the stack, which is probably 4 or 8 bytes, now has 0 or null pointer. Okay, so I have lost contact of this graph which is on my heap. However, these locations are still being engaged and organized in this way. Okay? So this is in some sense a memory leakage. So I have lost contact of a data structure which is there in the heap, and this is irrecoverable during this run because I did not store 5000 anywhere else. So memory leakage comes when we lose memory which is holding data which is of no relevance but has not been released explicitly by it. So to avoid memory leakage, any good programmer will build up a data structure on the heap as big as he or she wants. But before deleting this, it will not do like this. It will take this pointer, delete or remove each one of them and make it free, and then it will delete it. So memory leakage is the unintended losing contact with a data structure which is there on the heap. And the heap is dynamic memory. The heap is never restored unless somebody explicitly removes it. When the program terminates, the heap is empty. But if your program is running, everything that you kept on the heap is inaccessible except using the pointer or the address through which you have it. So leakage of memory means basically I have memory, but since I have not done things properly, I do not have way to access. I assume this is what leakage is. Is there any other alternate solution to avoid segmentation error? Now this depends on your, so this is the question by Neelam. alternative to segmentation error. Okay, so one alternative could be we can become very pessimistic, which means that if I ride in a car, I may get into an accident, so I'll never ride a car. Okay, then you will never have an accident with a car. But that's not the way to do things, right? So what it essentially means is segmentation faults are a natural process through which things are happening. They're typically happening because of pointers by and large, okay, and basically access any way you want to access to memory which is outside the space of the process. So if one is a careful programmer, they will use pointers with a lot of care and make sure that the objects you are pointing to are actually belonging to my area. There are ways to do that. So ensure good usage of pointers, good usage of arrays. Don't go and access elements beyond an array. So when you refer to arrays, do it carefully. And what do I mean here? Good usage of pointers. This essentially means dereference a pointer with a lot of care. Make sure when you are dereferencing it belongs to your area. So dereference a pointer has to be done with care. You cannot go and ask what is inside somebody else's area. There are languages like Java who do not allow you to define a pointer. They have a different implementation, so you will not have this problem. So generally, if you are working with C, and that's what I was told that all of you want to work with C, then C does not give you too many safety measures. If you want to use pointers and C, as I showed you right in the beginning, C is very loose with checking. It says, okay, pointer to one thing and pointer to another can be mixed up, and a result of which things can happen. So to avoid segmentation error, you have to make sure that you make good use of those entities which could give rise to segmentation. Okay, so make sure that you always access to addresses within. What is the function of multi-pointers? I don't know what this is. What is double free bugs? Not relevant here, I'll ignore. Star P plus plus and plus plus star P are same. Okay. Now, all the answers I will not give you, but I'll give you pointers to where you can look at it if it is relevant. So this I sort of hand waved long back. I probably discussed it the last time. So somebody is asking this question, and you can have any such expression. You can have any such expression that you have. So somebody writes something like this. Obviously, we don't know what is commutative, what is not. So here observe, when you get an expression like this, observe that there are two operators. What are the two operators? In each case, one is the star, and what star is this? These are dereferencing star, not the multiplication star, because it is used with a pointer. So take P, star P means go to the address which is contained in P and look at that object. And plus plus is a unary operator, which is basically pre or post increment. So here it is pre increment because it is coming first, and in the second one it is a post increment. So I am telling you the general rules. You should figure it out. If you cannot find out, then you can ask me in the next class. So what you should do when you get this is, please consult the C++. There is a table which I had given you in the previous slide, which is called the operator precedence table. This is fixed for every language. Java has its own rules. C++ has the rules of C and something else. So since you are interested in C, please go and look at C. What will it give you? It will give you three properties of any operator. One is called associativity. The other is called precedence, which probably comes here. Okay. It gives you the arity. You should be able to read the table. Okay, and that's it. And the operator, of course. So these properties of the operators, or they are known as attributes, dictate how an expression is evaluated. If you know it, great. If you don't, so I'll give you both the options and you figure out which is correct. So let me arbitrarily assume, which may or may not be correct, that plus plus operator has a precedence value of 20, okay, has associativity from right to left, this is called right, I'll give you, and arity is 1, which means it takes only one operand. Star is another unary operator, Arity 1 means it takes only one operand. It's a unary operator. Binary operator will be 2. It has 2 operands. And let's say star is also right to left, and it has precedence value 90. These are fictitious values. These are not correct values. So you should get the correct values from the language rules. Now if I take this and try to interpret the first one, what is star plus plus? Why is the confusion coming? Because somebody has not given a bracket. If you change this, instead of this, if you write star p followed by plus plus, the rules of the game are clear. You must first dereference p, you will get an object. To that object you do a plus plus and produce a value. Okay? If somebody wrote star of p plus plus, then also it is very clear what is to be done. First I take p, I increment the value of p, I produce a new pointer which will point to a different object than p, the next object perhaps, dereference it, I get a value and give it that value. But what happens when there is no parenthesis over here? Then one uses the rules of this game. So this one says plus plus is at a higher priority, 20. So this will be interpreted like this. However, if I reversed it, then it would have become like this. So read the rules of this game. Whether it is right to left or left to right is also another property I don't want to confuse with. So if this is the interpretation under my given explanation, then what will happen in this case? Star p plus plus will look like a strange thing. Suppose p is pointing to some value, let's say 1000, which has the value 10. I'm assuming pointers to integers, which may not be. And this is, let's say, 1004, which has the value 15. And then I do star p plus plus, and my interpretation was this is higher, so I changed it to, for internal purposes, it's like this only. I'll first do p plus plus. So p is 1000, p becomes 1004, you've done it already. So this goes, p becomes 1004, and then you dereference, you get the value 15, this answer. If the reverse was true, what would have happened? I would have interpreted it like star p plus plus, if star was higher precedence operator. In which case I'll take this p, I'll redraw the picture. This is my value 10, this is the address 1000. Okay, I will not do p plus plus. So when you do star p, higher precedence operator, dereferencing is more important. If the language says, then I get the value 10 out of this. Now when I get the value 10, what is 10 plus plus? This will be a compile time error. Figure out why. A constant cannot be incremented. So the system will throw you out. Okay, so whatever. So basically, coming back to your question which you asked, if you want to understand with pointers, you can write any complex expression that you want. Go and consult the C operator precedence table, look at these properties and very systematically parse this expression according to the property. You can put brackets, then interpret. That is the only interpretation with the compiler will also. Okay, so what is heap? I'm going to discuss in a short while more, so I'll ignore that. So I don't know what is double free bugs unless you tell me what that is. I have not heard this term at all. Okay, so I think how many levels of pointers can we have? Yeah, this you can ask. So pointers levels mean this. Check out on your system, write a small program and check it out. So this question is saying is like this. Suppose this is something which is containing an address. Suppose I put the value 1000. This is an address. So here is 1000. This value is, let's say, 2000. So here is 2000. This has maybe a value 500. And here is my memory address 500. So what are these? Since 1000, this contains the address, is basically pointing to this. This contains an address, is basically pointing to this. This fellow is pointing to this. Actually, this can all the way back point to this. So I interpret your friend's question, Chiranjeev, by saying how many levels? So how many times I can do this? Okay. So is there a finite restriction on the chain of pointers that I can create? So creating a chain of pointers. Pointer pointing to pointer to pointer to something. Okay. So what do you think the language will say? Any decent language will say, I have no restriction. Go ahead and do as much as you want. No restriction, none. However, I have told you that there is physical restriction in terms of memory. So if you create a chain of pointers in your static area, which is or your stack, if you may exceed the stack size by doing it, and then you will get an error. So a priori there is no limit, but depending on which area you are doing this, you may exceed the size of that by doing it again and again infinite, and therefore you may get into segmentation. So no preconceived finite limit, but they are restricted by the size of the data areas as decided by the OSN compiler. There is no other restriction. Where the pointers are being created. If you are doing on the heap, then restricted by the size of the heap. If you are doing it in the stack, then it's on the stack, and so on. Okay, so let me resume back. Okay. So what is heap? I have not done. I'll do it in a short while. Can we subtract or add pointers from each other? The answer is yes, you can. I'll again ask you to find out. So this basic C. What kind of operations are permitted on pointers is a more correct question to ask, or more sharper question. You should be able to answer this. What all operations are allowed on pointer data type? This is a more genuine question. So the point is, what your friend is asking is this: like suppose you have int star p1 comma star p2. I create two pointers to integers. This is declaration. And then if I do p1 plus p2, if I do p1 minus p2, if I do p1 plus 10 p2, okay, or if I do p1 modulo p2. So there are so many operators which are allowed. Which of these are legal and which of these are not? So one can answer one way by going into the C language reference manual and checking it out. The other way will be to think logically. So for example, if these addresses were indeed addresses of houses, okay, genuine houses on some street in some part of the city. I'm not drawing the houses very nicely, but assume these are houses. Okay, so you know the address of this, 235, this street, whatever. And this is, let's say, 431 on the same street. I'm ignoring. If somebody says, I want to produce 235 plus 431 and therefore produce 666 as a new address, there is no guarantee that firstly such an address will exist. It doesn't make sense. So mostly in the address world, taking two addresses and adding, multiplying doesn't make sense. What would make sense? I know 235 and I can say 4 houses away, please take me there. Or it is 10 houses away. Okay, so observe, what am I doing? I am taking an address, and to that address I am doing plus minus a constant. I want to go a few distances away. This typically is always allowed. Okay, so only those operations which make sense in real life will also make sense in the computer life. So addresses you don't multiply by arbitrary operations. You can compare. Is 235 equal to 235? Yes. Is 235 less than 431? Yes, you'll do that. Can I go a few things up or down? Yes, you can do that. So pointer arithmetic, as it is called, it is there on some of my slides earlier, is restricted for a very good reason, that you otherwise produce meaningless entities. An integer operated with an integer typically gives you a meaningful integer or gives you true, false, whatever, but addresses typically don't do that. So all I'd like to say is figure out, these are already defined by the language, very restricted. You cannot do any arbitrary stuff. And whatever you need to do typically will always be perfect. Given an address, you can produce another address in a meaning. Can the size of an array be declared at runtime? Okay, so there are a lot of questions coming in. I have to move away, but let me take one or two more. So size of an array be declared at runtime if you want to do. I have to give the question, the answer to the question in both in a yes and no manner. So now it's very important which area are you talking about. Okay, so hopefully it may clear somebody's things also. So why array? Anything. Array of okay, controllable size. So array of a certain size, this you want to do at runtime. So typically in the most generic scenario, the answer is no if you want to do it on the stack. If on the stack, no. In the heap, yes. So heap is a runtime allocation, so you can always do whatever you want, but you cannot do it on the, okay, so which means you cannot have a fixed data area, you cannot create something which is not fixed because you are saying you want the addresses, you want something of a variable size. So yes, you can do it, but then you have to do it in a different way. Typically arrays are supposed to be statically declared, held in the stack, and therefore they are not done. To maintain your requirement, languages have defined different classes. For example, look at the vector class of C++, okay? Or you can create your own class or struct in C where you can do all these things. But native support, the answer is how to print 2D array elements. Maybe we can do this much simpler. It's not a big deal, but we can look at it. This is the last question I'll take from Selvaraj. Suppose I is an int stored at address 1004. What we will get as output if we dereference address 1006. Firstly, you realize that it's not very easy to do this. So his question is this, if I write the question, let's say here is P, okay, and what is the P is an, so I'm assuming in my machine thing that int is of size 4. If the int is of size 2, then the answer is different. So let's say P is holding the address of some integer, maybe the value 100. This, let's say, location is 2000, which means the value stored in P is actually 2000. Okay, so this is what it is. Now he says, what happens if I dereference 2002? Okay, so first you should be able to ask the question, can I dereference 2000? Because P was not created by us, remember. Well, how did I get this P? So maybe I did int I equals 100. So I created this, the box with 100. Then I did int star P, which is equal to address of I, and therefore I got this 2000. Now since P is known to be an int star, only way you can move with P is in units of 4. You can produce 2000 plus 4 minus 4 plus 8 minus 8. You cannot produce 2002. There is a restriction. A pointer is bound to the size of the object. So only increments to P that you can do is on the type of the object it belongs. However, if you change the question and say if it was a short, then the answer goes different, because shorts are 2 bytes on my machine. So for using a short, you can generate 2002 from 2000, and therefore get dereference. Okay, so the point here is you cannot dereference 2002 unless you do some low level golmaal, which I am not going to teach you, but you can do it. There are features in C which uses unions and so on, by virtue of which you can do what you have stated, but not directly. But if you are allowed to, the question was, so I'm saying it is not very easy to access this using the P that you have done. But there are ways of doing it. There is always an escape clause. So in case you really wanted to see what would have happened. So this is 2000. Here is somewhere 2002 in the middle, and this of course, so the bytes allocated are 2000. You should check it out, 2001, 2002 and 2003. This is the last byte for an int entity. Okay, suppose I put into the value, to this the value 2 to the power 17, whatever the value is, calculate and figure out. So 2 to the power 17 is lots of zeros, 16 zeros, and then a 1 out here. So this is how this value, whatever I have stored, will be put out in a bit wise inside this entity. So now if you go to 2002 and try to see, you will see whatever bit pattern lies to the right. Now this is because I told you it's int. Had I not done this, but I would have done something like float x equals 3.5 in the same data area, this is 2000. So x, bits of x were laid out here. If you know IEEE format, then it is fine. And then if you want to see at 2002, you will get whatever is stored out here. So it depends on the data type. If it's a car, the data type pattern is different. For integer, it's a proper string. Float has a different representation. A pointer may have a different representation. So if you want to go in the middle and see, you will see what bit pattern the compiler has put inside that place, and you will see from the middle whatever. Okay, but what value you will see is a different cup of tea, which I'll skip. It depends on what P is a pointer of. Okay, I think let me go back to my original theme, otherwise I'll miss out. So let me resume from where I was doing. So what I immediately wanted to do after, I'll skip some slides. Okay, let me skip them for a moment. So I'm going to skip 21, I skip 22. So I want to first take you through application of pointers. So characteristics of array, slide 23, please read up. It's not very, it's only there for completeness. I don't want to look at it. Some issues are there, read up. If you have doubt, ask me on Wednesday's class. Read up class, slide 27 also, 28 also. These are simple stuff. I want to get into the data structure parts. Okay, so which I want to show you. So where are pointers being used? Pointers typically in C are used to create structures like this. I'm on slide 30, and you can see some boxes connected with array. So observe that how many boxes are there in this list is completely controlled by the user. Okay, and when you create such structures, they are called linked lists. So they are like wagons of a train which are connected for one particular journey, and they can be disconnected later for a different purpose. So in this picture, observe the size of the list, which means how many boxes is not known while the program is compiled, is not even known to the writer of the program. So the runtime data will decide how many boxes. So what happens? The first conceptual view that you should have here is the boxes are actually on the heap, and I have to open up the heap over here as I go along. But the head that you see is essentially something on the stack, which means that I create a head of a list, or I create a place to store a pointer of a list in my stack area, but the list physically resides on it. This is the view that I'll come again and again, but keep this picture in mind if you want to look at it. Again, I'll put this very clearly for you. So if I draw a linked list, I'll draw it a little more detail here. Suppose my head is 5000. Here is my heap, which is a totally different part of memory, completely controlled and dynamic. So here is 5000. It may have a value, let's say 20. It may point to an arbitrary area somewhere, could be 6000, 7000, which has the value 12. It may go back to another point of the area, which would have the value 100. And this may come to another part of the area and have the value -5. And here is the null. So in this area, which is called the heap, we are creating elements and linking them up. And from the stack, which is what I would like to show here, in the area of the function who is creating this, there is some function running over here. This is the way you link or hold the address of a linked list. So the physical place is somewhere, and I only have the address. Okay, so imagine your ATM card with you. It's not money, but you go to a teller or ATM machine, and there you can withdraw your money. So you only have the access to the first element of the list, or where the list begins. The rest is all hidden inside this. So first point is, why are such collections, or why are these organizations useful? And that's what I'm trying to answer first. Why are such data structures useful? Okay, so depending on which year of study you are in, depending on whether you have done courses on compilers, databases, operating system, data structures, and so on, you would have some answers, but I'll try to give you the answers in my own. So I'm giving you now examples of data structures. This is on slide 31. Okay. I won't have too much time, but I'll just briefly talk about. And if you have questions about this, please put it as I go along. And in the last 10 minutes or so, I'll try and answer each one. So you see a linked list here, which is organized in a bottom to top manner, the way a plate of stack of plates are kept, or things like that are organized. Or you would have seen trolleys in an airport or in a railway station. They're put one inside the other. This is a stack of. You can see these boxes, and you can see that one box is above another box, and so this data structure, the word stack, which I use already in the hardware, is also supported by software. There are many programming problems which require a stack to solve them. Okay, I won't have time to discuss them here, the problems themselves. But wherever you want to use a stack, and you are not sure how many elements will be in the stack, whether it will be 1 or 1 million, we typically use this linked list design. So I'm showing you the linked list on that slide. which is 31. So if you want a linked list, if you know a linked list, you can easily create a stack as a linked list data structure, code the operations which are required for a stack, typically which are push, to put an element in the stack, remove an element from the stack, look at the stack, and so on. Okay? So stack, which is a concrete data structure, is often built upon linked list. These are actual data structures. Similarly, a queue, we have used this great. I have some examples later. A queue is a linked list, which is very funny. It has two ends, a front and a rear. Just like a real queue in which we often stand at various places. The person at the front of the queue has a direct access. This is where the services are done. This person gets serviced. He's at the front of the queue. And if somebody wants to join, they join at the rear end. So front and rear are independent of each other. The front gets serviced, leaves the queue. The person joins last, joins at the rear. Queues are again a very important data structure which are used in solving many problems in computer science. So again, look at the linked list manner. The only difference here is it is a linked list with two headers or two access to the list at two distinct locations, the first and the last. After that, I have a tree. So this is how a tree looks like. Again, look at the main theme over here for me is that these are all linked collections. There are pointers, one or more, which are inside a data item through which a complete data structure is built. We have seen a binary tree. Observe that this is a way a linked list can realize a binary tree. The only difference here is that each node has at most two children. So a node may have two linked fields or two pointers inside. But again, if I know linked list and how to manipulate, I can create a tree and also manipulate. Similarly, I have shown you a few more. I'm going to skip. DAG stands for Directed Acyclic Graph. These are multi-rooted trees. And what happens in a DAG which cannot happen in a tree is that a node can have two predecessors. There can be two pointers to the same node, or a node can have two parents, which is not allowed in a tree. It's another data structure and most frequently realized using linked lists. That's why it's here. This is a very popular data structure called a hash table. Again, you observe that there's a linked list hanging around somewhere. Okay, and this is a very interesting and efficient data structure which is used for searching. Okay? Maybe I'll take a minute and explain this. If you have not seen it before, it's quite useful. So suppose I want to illustrate a hash table for searching. So observe that hash table has two distinct components. One is an array, which I've shown out there. I'll use this array. This is only an illustration, so don't take it very seriously in that sense. And you can give me, so this is meant to handle searching in integers. Since I have no idea how many integers you will give me, only then I'll use a hash table. Otherwise, I'll use an array. So suppose you keep giving me integers. You give me an integer I. What we do is this. I create a hash function or a function which does this. I modulo, I'm going to use a prime number. I've used 5. So what does it say? Take any number I, divide it by 5, take the remainder, and this is the value of 5. So now you give me numbers. Suppose you give me 23. So I'll do 23 modulo 5, which is 3. So I'll take the third list and I'll put 23 here. So now let's say you give me 21. 21 has modulo 1. So I'll put it in the list which starts at. So essentially you can see this list will keep building up, and the common property of these lists are that they all have the same remainder when divided by this prime 5. Okay. For example, 3 will be here. For example, 38 will be here. They all have remainder 3 and so on. This will be 1. So this could be 6. It could be 151 and so on. So what am I doing? You give me an arbitrary integer value. This is what the typical power of a hash table. So take an integer value. You produce an index by doing this hashing function. This gives you an index. This is bound to lie between the range 0 to 4 or 0 to p minus 1 if you take p as a prime. So I take an integer value depending on what is the index. I just keep loading it there. What is the advantage? You give me any number. Suppose you give me the number 102. And you say, is 102 already? Search, please search for 102. I'll take 102, do a modulo 5, and I'll produce the value 2. I'll come here, these are all null. 0 means nothing is there. So I'll come to 2 hash table 2 and I'll say there is no entry there. So 102 is absent, is not present. Observe this data is not sorted. I'm not doing anything. No binary search, nothing. I directly produce an index, look at that index, it is there or not there. If somebody says, please look for 33. So I'll do 33 modulo 5, I'll produce the index 3. I'll pick up the list at 3 and keep examining. 23, no. 3, no. 38, no. End of the list. 33 is absent. So now you can see the power of this organization. Since it uses an array, you can very quickly go to the list of your choice which you want to search. If an element is present, it must be present in that list only. Okay? So I have to only search for the size of the list which is hanging out here. If present, I've found it. If absent, it is not. So this speeds up search considerably. It's found to have excellent performance in practice. For example, I'm a compiler writer and many of us use hash tables to do ours. Okay, so this you can see. If you look at this data structure now, you can use it in any which place. It's an interesting combination or a hybrid of an array and a collection of linked lists, not one linked list, many linked lists, each hanging at one array position. Okay, similarly, if you, so this is an example of a linked list as a graph. I don't know if it makes sense to you. So the way you access, again, observe there's an array in the middle. That array is indexed by vertices. Okay, on the left side, I have predecessors of a node I, and on the right side, I have successors of node I. What does it mean? If you ever have to use this. So let me draw a very small graph and show you how it will look in this data structure that I'm trying to propose. So let's say I have a graph which has 1, edge to 2, edge to 3, and there's a 4 to which this is what it is. So I've drawn a graph. So I hope you can see that. I have drawn a small graph over here. So this graph, suppose I want to represent in my data structure. First, remember, none of these data structures are unique. Okay, you can design your own one depending on what graph you have and what graph you want to process. So my data structure which I am suggesting here, which is of intermediate complexity, will create an array equal to the number of nodes. So I'll get an array of size 4, and ignoring C, I will label them as 1, 2, 3. So now I look at the successors. My successors are on the right. So I'll put a linked list here. Who is 1 connected to? Now 1 is connected to 2, 3 and also 4 directly. 1 to 2, 1 to 3, 1 to 4. So I will create an edge to 2, to 3 and to 4. What is common between them? That they are all direct edges from 1. So 1 to 2, 1 to 3, 1 to 4. Okay, now let me look at predecessors of 1. Is there anything? So I have two lists out here. One which takes successors and one which takes predecessors. From where can I come to 1? It doesn't have anything, so let me add 1. So here is I'm going from 4 to 1. So predecessor of 4 of 1 is 4. So I'll put a 4 over here and I'll say null, no more. That's it. That's the only predecessor. Similarly, if I look at 2, 2 has a successor 4 and that's the only successor. So I'll put it on the right. 4 and this is the end of the list. 2 has one predecessor which is 1. So from 2 I can go to the predecessor 1 and close the list. Similarly, if you fill up all of this, you will see a graph data structure emerging in which we can tell you, if you want, whether an edge exists from one node to another or not by searching in this data structure. So this is my simple view of a graph data structure. And what I can ask questions about in the graph data structure, is there a path from 1 to 1? It's not obvious. From 1 to 1, I can go from 1 to 4, then go from 4 to 1. I can go from 1 to 2, 2 to 4, 4 to 1. So I can make a lot of queries and I have to write algorithms to answer those questions on the graph. Whether a path exists, what is the shortest path, what is the longest path, okay, the number of nodes in a given path and so on and so on. So if you want to go back to a graph data structure, okay, so there is very intense on the number of linked lists. And why linked list? Because I don't know how many successors a node will have. The graph could be changing. No more nodes are coming, you are connecting. Nodes are leaving, I am deleting. All that should be possible in this data structure that I did. Okay, so I'll skip this. If you have doubt, ask me the next time. I'll give you another interesting data structure which is typically used by, this is on slide number 39. Look at slide number 40. I'll just take 1 or 2 minutes to explain what this fancy looking data structure does. Again, observe it's an array on one side and there's a linked list hanging out at each array position. Even more non-trivial is the fact that this linked list is a circular list. So I go from one element, I reach a certain element, and I go back to that element. These are called circular lists. So there is a circular list hanging out at each array position. There is another thing which is happening below. Okay, so each node is looking horrendously complex, okay, but it is actually used by operating system to handle all our disk transfer or disk traffic between the memory and the disk. Okay, it's a very popular, a very efficient data structure. So I'm only looking at it as an implementation of a slight complex linked list. Now if you go to one slide before and look at slide 39, you can see what the intrinsic structure of one node in this organization is. There are 4 linked fields. So one says who is my next neighbor who follows me in the same queue, who is behind me in the queue. Okay, because each array position is supposed to be a queue, it's a circular queue. So each element knows who is the follower in the queue. Each element knows who is its predecessor in the queue is, who is ahead of me and who is behind me in the same queue. And there are 2 more pointers. It says who is behind me in the free list and who is ahead of me in the free list. You observe that this says that one node has multiple membership. It belongs to a queue and it may or may not belong to a free list. Okay, what is this free list? The free list says I have some wagons. Some of the wagons are occupied and some of the wagons are free. Those which are occupied by disk block data. Okay, which means some process is accessing that particular disk data, has asked for it, and therefore it is in a particular slot or wagon, as I call it. Now suppose I have 100 slots, that's all that I have. And a request for 100th disk comes, which is disk data or disk block, which is not there in my collection. But the process has to be serviced. I have only 100 slots. So what do I do? What we do then is, what the OS could do is, it could figure out the disk block which is not currently used, write the disk block on the disk, free up a particular slot, and in that it gets a new disk block. This is like a cache. That's why the word buffer cache. So in order to facilitate disk transfers, disk blocks indexed with numbers, okay, you can only keep a certain few disk blocks in RAM or in memory, the rest is in disk. How do you facilitate minimum disk data transfer and maximum service to all processes which are working together? Okay, so the OS has worked out this efficient structure. It is a multi-linked list, as I showed you on the next slide. Things are organized in queue because I want to know who has been there in memory for a longer time, who can be evacuated, and the slot released for another request. Okay, so when you know the problem, you'll appreciate the data structure, but look at it that if you know how to handle a circular linked list, and if you know how to handle an array, the rest is sort of easy. So there are some more data structures which I'm going to skip. You can read them at leisure. What I will do in the remaining few minutes, first let me, since I may take questions which you would ask, and that's more important for me. After that, what I've given you is, since the slides are available with you, I've given you a design of a singly linked list. Okay, so I'm going to work here for 5 minutes, and without explaining the design in great detail, hopefully if you read through whatever I have written, you will be able to appreciate the design, try out alternative designs, make changes. If it gives segmentation fault, no issues. Okay, you should be able to correct that and thereby learn how to manipulate single linked list so efficiently that you can design any data structure of your choice. So first, some basics about the linked list design. The design I have given is nowhere complete, nowhere the best. So please read it carefully. And before Wednesday, which will be my last class, I've given it to you to chew up the design, understand. But the spirit of the design I'm going to show over here. So what do we want to create? This is my stack. Okay, some function would like to create this. This is the stack. And therefore, I will only concentrate on one entity. I'll call it the head of the list. Okay, the first element of the list. So here is the head. And what we want to do is we want to create on the heap a linked list which can be anywhere in memory. I'll draw it consecutively, but that's not the thing. It can be as big as you want, we don't care. At the end of the list, I mark by this symbol, actually it will be a null address. So this is the heap, the huge area typically. The list is on the heap and I want to create this. What is the point? The point is if another element comes, I want to add to the list. If I want to find out how big my list is, I should be able to support that. So basically what it turns out is, how do I create and manipulate such a collection? Okay, so I have of course tried to influence you by my design, but you feel free to do something different. So this is what I'm going to say. In general, without getting into C, we should first conceptually decide what do I want to do with this collection and how do I do it. So what we typically do is I have to first decide a data structure which we'll talk about later. But let us think of some operations which I want to do on a linked list. This is very, very important. Typically the operation that wants is how do I create a linked list? I'll decide this, how to create, but you must know how to create. We must, all of us. Once we know how to create a linked list, this will typically create an empty list. So I don't know whether anything will come at all or not. All dynamic data structures start by an empty creation. So we create an empty list and this is what we like to implement. Once I've created an empty list, I want it to grow. So I've given you several operations over there. One is called a push. The push will add an element at top of the list, front of the list, at the head of the list, whatever you want to call it. I'll give yet another operation I given which is called append. It adds an element at the end of the list. Let's call it L. I'll give it a name. So front of L, end of L. I can also keep my list sorted. So I'll create yet another operation insert, which inserts an element in a sorted list in the position. And keeps it sorted. Typically people talk, you can use any operation, you don't have to be constrained by what I am saying. This returns how many elements are there, typically called the size of a list. You need to show what is there in the list, so you need to create a display operation. This is called traversal. You want to traverse a data structure, walk through the data structure. So I want to traverse the list. Okay. I may like to find an element from the list. So find L comma V. Okay. So search the list, the searching operation. I may like to remove an element from the list. So maybe delete. Okay. Delete element V from V. Remove an element. And you can see I can keep building. I can keep building this operation list as exhaustively as I want. I've given you more on my slides. You can join two lists. You can break a list, right? You can remove duplicates from a list and so on. You can just decide. You find given two lists, you want to find the difference, like I said. So the operations could be as rich as your application demands. Nobody can tell you what to do. As rich as required. And what would the linked list design do? Basically implement these operations and choose a data structure which will be doing this. So that's all any linked list design will do. Once you can do this linked list design, you can take your design to the higher level and design other data structures, what I had given, queues, stacks. So let me point you out to slide 46. I'll spend maybe about 2-3 minutes more and then I would like to take your questions. This is how I'm suggesting in C you define a linked list. Again, it's not unique. Okay? So typically when you create a linked list, you like to have the flexibility that I can create a list of integers, list of floating point numbers, maybe list of students who have multiple attributes, name, roll number, maybe something else. Okay? A list of whatever. So list of various types of data values. So the first one that you see, if you're familiar with C, it says type def int as item type. So int data type, which is a built-in data type, is renamed by me, that this is the, I'll call it as item underscore type. It's just renaming another name. Why do I do it? Because later on my program will use only the name item underscore type. If you want to change it to a float, just change this declaration to type def float. If you want to make it a struct, make that type def struct as an item type. So you can have one data, multiple data, and you can use this generic way of creating linked lists of one or more data. So the purpose of this type def is to say that I will write in my program item type. Whether you want 1 value or 10 value, you manufacture that with this type def. The next one you observe is a struct. This struct has item type info, but item type for this implementation is an int, which is fine. So I have an info field which is an integer, and since I assume you know C, struct item tag underscore next is a pointer which points to block like this. So this entire struct item tag I want to call by a simple name list item. So I don't want to repeat this again and again. So the type def allows me to create this box with one integer value and one pointer and name it as list type. And the last type def says that list type is yet another type name. It's not a variable, it's a type name which is a pointer to the above. So using this, I will take only one or two, the rest you can work at leisure. So what would be creating an empty list mean? So I want to do like this. If I want to create an empty list, I should always distinguish between my stack and the heap. Okay. So what do I declare in my main program? Assume that I have declared all these three things. I have list underscore type, which is essentially a pointer to list underscore item. So the names are very arbitrary, don't worry about them. And list underscore item is basically these boxes, which is the type name for this, and item type is the type name for it. Okay. So if I want to write in my main program, how do I create an empty list? The solution that I have proposed, which you may or may not agree with, is to say that please create a list type entity, because this type is given, and call it L. I can do this. Okay, this is my intent. So what will happen? On my stack an L will be created. And what is list type? Now look inside, it is basically a pointer. So this will point to something, we don't know where. It's typically capable of pointing to a box like this, and this box has been created. So there is an L value for it. Then what I want to do is I want to call this create and give it this address L. Why address L is I'm going to explain. I will not explain each one of them, I explain a few. So what do I want to do? If I want to create an empty list, typically this should point to something on the heap. But I want to create an empty list, there is nothing on the heap. So my implementation really which I want is that once I declare this place for L, I want to put a null here. This is what my create will do. So what does my create want to do? What do I give it to create? So create as a function will take a pointer like this. Okay. So what is this? So this contains a pointer, but I want to change this address itself. I want to go to L and change its content. And what is L? L is the address of this whole thing. Okay. L is the name of this, but I want address of L. So basically what L requires, or to change this, I need a list underscore type entity's address. Okay. And it's void. I don't want to do anything. So this function just returns a void. And what it's trying to do is taking a pointer so that I get the address of L. I don't want L. L is this, but I want address of L, which is this. And then I can change the value to null. So if you look at the implementation, which is a few slides away, you see this. Void create list type star list PTR, which is very, very important. Why I have written like this. And it takes, so list PTR is what? Is a pointer to list type. If I dereference star list PTR, then I get to the content of L, which I written there, and put it null. So to do this, what I did on my slide, as you can see, my list null, I want to do. So it's a style. I have decided that this is how I will write my code. So I've decided the signature of void create, and I know by create in my main program, if I write list type my list, the first one, define void create as a function somewhere, then create and my list will create an empty list with. So I leave it to you here. I'm giving you about 3-4 days to look at all these slides, come back with all your doubts, and then we can not only look at the design I have given, but also I would like to improve the design with your help when I come back the next time. Okay, but this remaining time, whatever I have, I would like to see what questions you have placed for me. So again, repeat, the homework is please read the remaining 20-25 slides, look at all the operations, come back with more operations and doubts if you have, run the program, check if there are errors, and raise all your questions when we meet the next time. If you can do this design properly, understand and improve it, you should be able to, in principle, look at any other. So let me quickly see what your questions are. What is the peep operation in a stack? Okay, it's not called peep, they call it actually peek, but it's roughly like a peep. So without going to my pages, I can tell you. So suppose you have a stack of plates, right? Now typically what you do on a stack, you put a new plate on top of the existing stack, or you pull out the top plate from the stack. But suppose somebody says, you give me the top, I want to take a plate which is only from Corel company, supposed to be very nice designers. So what do I do then? I don't want to pull out the element because this fellow may not like if it is not Corel. So what I do, I will look into the stack, I look at what is there on top of the stack, but I will not pop. So I am neither pushing, I am not popping, but I am just looking at the top element of the stack in order to take a further decision of operation. That is called a peek. So a peek is exactly like a pop, except that the physical pop is not. So you return the top element of the stack without deleting it from the stack. This, for incidental reasons, they have called it PEEK as an operation on the stack, which is a non-destructive operation. It's a read-only operation on the memory leakage. Function of multi-pointers. I hope I have told you multi-pointers are used to implement different complex data structures. You need more than one successor, predecessor, graphs, DAGs, hash tables, and so on. How many level of pointers have I answered? In which application singly linked list is preferable? So to answer this question from Archana, singly linked list, I'll ask you to look at the assignment problems I've given. Okay. And there you can see that there are some operations which typically use a single linked list. I've given you a programming on polynomials where you can use a singly linked list. Okay. And all the operations I showed you, a hash table is typically a single linked list. So singly linked list and doubly linked list, the only difference is what operations you want quicker. If you want delete to be quicker, then people go for a doubly linked list. If delete is not crucial, which means you do delete once in a while but not very often, then a singly linked list. So for a doubly linked list or more linked list, you pay the cost of the pointer fields. Your every node becomes heavy. Single linked list is light, only one pointer. So people typically will do a trade-off, which will take less space and hopefully less time. Circular linked list and circularly header linked list. Okay, I think this is just a nomenclature difference. A circular linked list may or may not have a header. That depends on what you want. Okay, so if you want, maybe I can quickly draw the difference between for you. So circular linked list typically in our notation will be something like this, and your pointer points to somewhere. This is a typical circular linked list. Whereas circular header linked list will say you come here, okay, header has some important information about the linked list, and this could be a linked list. It goes to this. For example, the hash table will be like. Okay, so I think I'll stop here. We run out of time. If there is opportunity, I'll answer your questions on the forum itself, so you can get your doubts clear. Thank you and see you next Wednesday.